Hello, I am Mrinmoy Dhar. I am a research scholar from Mechanical Engineering Department, IIT Kharagpur. Now I am going to briefly discuss about CFD and CFD in multiphase flow. CFD full form computational fluid dynamics. So first question arises in mind, what is CFD? CFD is basically the analysis of fluid flow problems which may simultaneously involve heat transfer, mass transfer, chemical reactions, phase change, any transport phenomena, and that would be done by computer based simulations. So next question comes, why CFD? CFD has actually the ability of simulating real conditions. It can elucidate information even when performing experiments are difficult. One may argue that CFD has the strength and that it can generate data spread all over the computational domain, which gives deeper insight into flow physics and helps in better design, improving performance, efficiency. Another thing about CFD is that it is relatively inexpensive. That means if you are having one good computer, you can go for CFD simulation. So next question comes, when CFD? Based on this numerous advantages of CFD, CFD has got lots of widespread applications, starting from physical problems occurring in our daily life. It has got a lot of applications in industrial applications also. Here are few applications, common applications listed: aerodynamics of aircrafts and vehicles, hydrodynamics of ships, biomedical engineering for blood flow through arteries and veins, chemical processing for mixing, separation and polymer molding. In multiphase flow also CFD has got lots of applications. Here we can see that different flow patterns during multiphase flow obtained by CFD simulations, and here are other applications of CFD. Next question, how CFD? For CFD simulations, we are having many commercially available softwares like ANSYS CFX, ANSYS Fluent, Console, Star CD, freely available softwares like JDish, OpenFOAM, and you can go for developing your own code, in-house code. But in one thing common for all the packages are that all three contains three elements like preprocessor, solver, postprocessor. In preprocessor, you have to first define and the problem geometry, means computational domain selection. Next is you have to divide the whole domain into subdomains, means meshing. Then you have to select the phenomena or which will be chemically or physically modeled. Then you have to specify the fluids which are involved in the problem, and you have to obviously define the initial conditions, means pressure, velocity at initial times, and very carefully you have to define boundary conditions, means pressure, velocity at boundaries, means wall, inlet, outlet. And once this preprocessing is completed, you have to go for solver. For solver, different methods are there: finite volume, finite element, finite difference. Finite volume is the most powerful and accurate. Many commercial as well as freely available softwares use this. I am going to discuss about finite volume steps. In finite volume steps, it first integrates the governing equations of the fluid flow over all the control volumes of the domain, and then it discretizes the integral equations for converting into a system of algebraic equations, and these algebraic equations we can solve iteratively. And after the solution is completed, we go for post processing. By doing CFD simulation, we can analyze and visualization of solution like velocity vectors analysis, contour plots, streamline patterns, and many others. As our focus is on multiphase flow, so let's talk about CFD in multiphase flow. Here is the Navier-Stokes equation for two-phase flow. This same equation will be solved over the whole domain. Here rho is the density, u velocity field, p pressure, mu dynamic viscosity, g gravitational acceleration. This I stands for different phases, and this d is the deformation rate tensor. Here is the equation for deformation rate tensor. Next is a continuity equation. This is also common for whole domain. If the fluid is assumed incompressible, means rho is constant for a particular fluid, that time this continuity equation will become this. And in multiphase flow, we have the interface between phases, and at the interface balance of stresses are very important. Here is the balance of normal stress at the interface, this equation. Here this n term is new, n is the normal to the interface, then sigma is the surface tension coefficient, and k is the curvature at the interface. And for tangential stress balance at the interface, this is the equation. Here T is the tangent to the interface. These are the equations. Another thing about multiphase flow simulation is the interface capturing. For interface capturing, there are different methods such as volume fluid method, VOF, and level set method. Here I am going to discuss about volume fluid method. In volume fluid method, what we do, we define a volume fraction function f, which is nothing but liquid fraction function. A cell may contain only liquid, that times this f will get the value 1, and a cell may also contain only gas, that times this f will become 0, means there is no liquid. And cell may also contain both gas and liquid, that means the cell is containing the interface, that time this f value will lie between 0 to 1, and this f will follow this advection equation. So let us talk about a software which simulates multiphase flow. As Jitter is a open source software, freely available, and it has some unique advantages. So I am going to discuss about Jitter. This Jitter is basically a finite volume based Navier-Stokes solver. It has the advantage that it uses adaptive dynamic meshing. So let us see how it adapts dynamic meshing. Actually, Jitter, what it does, it usually contains square boxes for 2D simulation and cube boxes for 3D simulation. Suppose this is our computational domain, it will create a number of boxes based on the user. So here you can see the refinement levels. These are refinement levels. At 0 refinement level, one box will be subdivided into 4 boxes, and in the next refinement level, any of the box can again subdivide into another 4 boxes. Here you are seeing that initially one box has been divided into 4 boxes, and in the next step any box whenever required can divide again into 4 boxes, 4 cells. This way it will continue. As this is actually called quad-tree discretization. Using this quad-tree discretization, Jitter adapts dynamic meshing. In this way, I was talking about whenever requirement. This requirement will be based on volume fraction gradient. Whenever in the simulation there will be a gradient of volume fraction, means near the interface and near the wall. There in these positions, it will go for high resolution meshing. And another criteria is vorticity. When in the simulation there will be the generation of vorticity, that time Jitter will go for high resolution meshing. This adaptive dynamic meshing has advantage that it is efficient and having complete control, and it saves computational time as well as storage. Here we can see that a liquid droplet is spreading over a plate. So this is the interface. Here you can see that along the interface there is a high resolution meshing, whereas in the other areas there is coarse meshing. And we can also see that this high resolution meshing is evolving with the evolution of the interface. This is actually adaptive dynamic meshing. In this, Jitter uses the volume fluid methodology for interface tracking. As we know that volume fluid, we define volume fraction function f. This is the equation. I already mentioned this, and this has the equations for generalized fluid density and viscosity. Here one term f bar is defined. This is filtered variable. This is actually used for high density ratios. Suppose air water, here the density ratio is 1000, almost 1000. So there we use f bar, filtered variable. This is evaluated by averaging over the 8 neighboring values of f. Suppose here you can see if we are going for the measuring the f value of this cell, so it will go for averaging of this neighboring 8 values of f, and by that, using this f bar, it will calculate the generalized fluid density. When cell will be containing only liquid, that time this part will become 0 and it will get the density of liquid. And when cell will contain only gas, that time this part will become 0 and it will get the density of gas. Same thing for viscosity also. These are the discretized equation obtained by time splitting projection method. First term is the temporal term. second is the convective term. Then in the right side, first term is the discretized viscous force, second term is the discretized surface tension force. Here subscripts are the time steps. This star is actually auxiliary time step, and n plus half is the intermediate time step. The next is the discretized equation for this volume fraction function, and next equation is for pressure. We can see that in the first momentum equation we have not considered the pressure term, but this pressure term has been considered here. Here we have considered pressure for correcting the velocity field, and that resulting velocity will satisfy this continuity equation. Using these last two equations, we get Poisson equation which governs pressure field. This is the equations. So here are all the discretized equations. Jedish, based on this quarterly discretization, used Jedish multi-gate solver and solved it iteratively by Gauss-Seidel iteration method. So and this Jedish actually operates on Linux machine. For writing the pre-processing steps like computational domain selection, meshing, boundary conditions, these things you have to write syntax for Jedish here in a .gfs file. So I will show you how to write syntax file. For that I have taken one example from Jedish main site. Here is one example of Rayleigh-Taylor instability. In Rayleigh-Taylor instability, what happens? Two fluids are there of different density, and they are separated by sinusoidal interface. And here is that at the top there is heavier fluid. Here you can see that a simulation of Rayleigh-Taylor instability, and the heavier fluid is at the top. So this is unstable condition, and this mushroom shaped instability will develop in time. So for writing the syntax of this problem, here 4 boxes are used, and they are having 3 connecting edges. At the end of the code, there is written how the boxes are oriented. It is important to see here written that 1 to top means box 2 is at the or on top of box 1, and then 2 3 top means box 3 is top of box 2, and again written 1/4 bottom means box 4 is bottom of box 1. So these are the orientations of boxes selected at the start of this syntax. GFS simulation is a solver, and this is the syntax for starting. Then this time n equal to 1 means it will at the real time of 1 second the simulation will complete, and dtmax is the time step. This refine 7 is the, as I already mentioned, that refinement level. This is the 7 refinement level for initial time. And this variable tracer VOFT is the VOF of the volume fraction function, and this is the initial condition of the interface. By defining this T condition here, the this interface condition has been defined by this line. And as I mentioned that by vorticity criteria we can define refinement level. Here by based on vorticity it will take the 7th refinement level. Here you can change the refinement level based on your grid independent study in a specific problem. Next, for based on the gradient of this VOF means gradient of this volume fraction, you can choose the refinement level. Then the viscosity of here in this case viscosity are same. So this is the syntax for writing viscosity. Then this physical params alpha is this is for writing the 1 by density, 1 by rho is the 1 by T into the density of one phase and plus 1 minus T into density of other phase. This is the syntax for writing the source term, gravity source term, V minus 9 point. Here minus because this V means V is in the upward direction, but gravity is acting in the downward direction. That's V minus 9.81. These are the steps for generating output simulation files, and here nothing to specify about the boundary conditions. So I have taken another problem where I will show how to implement boundary conditions in Jedish. Here in this problem, this is the air water flow around and obstacle. In this problem, there are 3 boxes three boxes are oriented like this is here three boxes are 1 to right means box 2 is right side of box 1 and box then 2 3 right means box 3 at the right side of box 2. So, for first box GFS box left boundary boundary conditions means left, this is the left boundary for first box. At this condition the boundary condition BC Dirichlet P0. Here I would like to mention that in mathematics Dirichlet boundary conditions means you are specifying the value of a given variable on the boundary, and another condition is this Neumann boundary condition. In the Neumann boundary condition you are specifying the value of the derivative normal to the boundary of a given variable. Let us see BC Dirichlet P0 means here you mentioning pressure P equal to 0, Dirichlet B0 means V equal to 0, these are velocity components, W equal to 0, and then BC Neumann U0 if this is the x direction and this is the our boundary. So, they had del u del x equal to 0, derivative normal to the boundary, del u del x equal to 0. Next condition was BC Neumann T0, so now del t del x equal to 0. So, for other boundaries are for top equal to boundary, here it is a symmetric boundary conditions in this problem. So, just to write boundary and bottom also boundary, these are symmetric boundary conditions. Now going to the second box. In the second box again these two are connecting edges and top and boundary symmetric boundary conditions. So, just to write top equal to boundary and bottom equal to boundary. And now moving to the third box. In the third box right side this boundary condition you have to specify. Same way using the Dirichlet and Neumann boundary conditions, here boundary conditions are specified and Neumann dilute equal to 0. And top and bottom there are symmetric boundary conditions. This is the way to implement boundary conditions in the JDish. For further details about implementation of JDish, please visit JDish main page. This is the JDish website, and you can go through syntax of the many examples given in this page. And for the structures of JDish, you can go through these two journals. Now, Mr. Abir Chakraborty will demonstrate how to implement a multi-phase flow problem in COMSOL software. Thank you.
Hello everybody, I am Abir Chakraborty, a research scholar in IIT Kharagpur Chemical Engineering Department, working in the field of multi-phase flow. Today I am going to illustrate a problem of a two-phase flow in which a liquid two-phase flow through a millimeter size channel. The geometry will be, which I will be doing a simulation work, will be a T geometry. So, our problem is this is our geometry, a T shaped millimeter size channel, and we are having a two-phase flow downflow situations. And the fluid which will be used are toluene and water. Toluene is an organic liquid, water aqueous. Then the thing which will be I will be demonstrating you to all of you today is that with given conditions such as the inlet superficial velocity of toluene, which is 0.07 meter per second, and inlet superficial velocity of water the same 0.07 meter per second given, and the outlet pressure in downflow case, my outlet will be this outlet discharge at 1 atmospheric pressure. We will be calculating what we will be calculating what will be my flow pattern, what will be the flow pattern in this scenario in this given set of conditions, and also extracting some results in the form of graph, which will be pressure drop versus length of the conduit. So, here is a downflow. These are two inlets, and 6 mm ID channel is selected, and the length of this channel is 1.5 meter, 1500 millimeter, with the side branches at 100 millimeter. So, my dimensions is y, this is the y, and this is x. Y is projecting towards across the length of the conduit section. So, as we can see, this is a downflow situation. The thing which we will be doing is that we do not know about what is the flow pattern will be happening in this condition, and also what will be the pressure drop across this conduit. So, we will be utilizing the COMSOL software which is commercially available, CFD software which is COMSOL multiphysics, and we will be getting our results with the help of that. The thing which I will be taking in this question is I will be assuming a 2D geometry. Before starting COMSOL multiphysics, I want to say some words about it. It is newly emerged in the market. It is a finite element analysis solver, and what is the strong point of the finite element solver is that it divides the whole entire geometry into different small elements, and it integrates the governing partial differential equation over those elements after being multiplied by a weighted function. Generally, Galerkin method of weighted residual is used. The advantage of this is that apart from the other solving mechanisms, this finite element method analysis can handle very easily any type of geometry, whether it is a distorted geometry or an irregular shaped geometry. It can tackle with the same ease and simplicity as it can tackle with a simplified or a straightforward geometry. So, my assumptions in this simulation will be a 2D geometry. Wall conditions which I will give is no slip. The superficial velocity of toluene will be 0.07 meter per second, and superficial velocity of water 0.07 meter per second. The outlet will be at 1 atmospheric pressure, discharge will be happening, a downflow situation of two phase flow. So, before starting I want to say some steps. This is the simulation procedure. What we do first? Quickly going through it, first we make a geometry. We make a domain, specify our geometry, we unite it. After that, we give input materials, define the input material properties, then select laminar to select our on which model we want to study the situation. In our case, in taking 0.07 meter per second, the flow was laminar in the laminar regime. Then we specify the inlet and outlet boundaries, give the boundary conditions. Then after insert the gravity effect, then do the meshing part. One thing important is about the meshing is that by default this COMSOL multiphysics in 2D geometry chooses a triangular meshing. It goes for choosing the triangular meshing. We should select mesh after doing a grid independent study. What is a grid independent study? Actually, we in this grid independence test, we go on reducing the size of elements, the number or as a result the number of elements increases, and we see after which point the difference in our result has diminished or nearly diminished. It is based on your criteria, about the criteria of your requirement, that might be 0.1%, 0.2% as required by the question problem. So, we see after which sizing the effect of your grid or the mesh diminishes, and we select and we say that after this mesh it has become grid independent, and we select that sizing of mesh. After this, I want to start with the how we can solve this, take this problem with the help of and solve it with the help of COMSOL multiphysics. As we can see, this is a COMSOL desktop environment, and there are two selections are there. One is model wizard window, and the second one is blank model. Blank model we use in this condition when we want to prepare a skeleton of our model, and later we want to implement it with different functionalities, custom made or tailor made functionalities. We want to implement those models. For a specific problem, we will go on for choosing the model wizard window. I click on this model wizard window. As we click, we can see there are different dimension options, that is 3D geometries, 2D axisymmetric, 2D, 1D and point geometry. So, 2D axisymmetry is nothing but along an axis geometry is built, and that axis, the reflection of it, that geometry is taken along the other axis. It is a mirror image replica on the other hand axis. In this way the geometry is built. I will be choosing a simple 2D geometry here. So, as we can see, it has having different modules here. What is that? AC/DC, acoustics, chemical species transport for performing mass transfer calculations, mass transfer simulations, fluid flow, heat transfer is there, from structural mathematics, all are present. our field of region of interest is on fluid flow. We click on this fluid flow node and again click on multiphase flow. When I click on this multiphase flow, here I find different our models are present here, that is bubbly flow, mixture model, Euler model, two phase flow, level set, phase field, moving mesh and rotating machinery. If I am having a stirrer or something like that moving part in our geometry. So, this bubbly flow, mixture model and Euler model are used in that particular in those cases where we know which is our continuous phase and which is our dispersed phase. When we are certain about our continuous and dispersed phase or certain about what is my flow pattern can be, then we go on choosing these models. In bubbly flow model especially used for gas liquid two phase flow, and then the left ones are level set phase field, two phase flow level set, two phase flow phase field and moving mesh. So, moving mesh is used when we are doing problem on distorting geometry and the geometry is changing without any material being added or removed. In those cases, we will use moving mesh. The phase field actually this method uses is first solves two transport equations. First is first to initialize its phase field variable and the second one is to energy to solve for free energy and uses the approach of energy minimization to track the interface. The level set method is used in those cases where we want to track our interface with the help of fixed mesh, when the whole computational domain can be subdivided into two subdomains and which are separated by an interface. In those cases, we will go for level set method. When I click on this level set method, I get laminar two phase flow and turbulent two phase flow level set. As I earlier said, based on our Reynolds number calculation, if you put those variables, that is 0.07 meter per second, then diameter and the density, the viscosity, you will get a laminar flow. So, I go on selecting this laminar two phase flow level set and click on add. As I click on this add, in this checkbox our laminar two phase flow level set gets added. Then I click on the study node. Now, solver is asking for which study I want to perform. There are preset studies like time dependent, transient with phase initialization, and there are custom studies, that is eigenfrequency, eigenvalue, frequency domain, stationary. Eigenfrequency, eigenvalue, when we want to extract eigenvalues or eigenfrequency of a linear or linearized model. In those cases, it is more frequently used in electromagnetics question or those simulations. So, there is stationary study, transient with phase initialization and time dependent. Since I do not know what the flow pattern will be, what will be the flow pattern or how it will be changing with time, I go on selecting a simple time dependent study. So, I select this time dependent study and click on done. As we can see, this is a COMSOL multiphysics environment. Now, global definitions part. This global definitions node, when we want to specify some variables to our system, we name the variable here in this checkbox. Suppose I write here type in something like omega or something, we give the expression here and then the unit, and later we want to call this variable in our field of study, or that is in our region of study, that is two phase flow level set. We want to implement in the wall conditions, that is vibrating wall or something like that, or initial values or outlet inlet, as the case may be. So, I go on selecting geometry, I click on this geometry. When we will right click, we will find different options here, starting from circle, ellipse, rectangle, square, polygon, etc. Projecting a 3D geometry circular channel on a 2D surface, it will be a rectangle. So, I select a rectangle. Now, this width will be this rectangles, this width will be the rectangle that our geometry ID, internal diameter of the tube. So, I select this as width as 6 and height I gave it as 1500 and select on build all objects. So, as we can see, this geometry, there is a rectangle has been built in our this box, geometry box, graphics box, as we are seeing. Then we go again on making two other geometries, click on rectangle 2 and we give this as width 6 and height 100. This is basically this part of our question. The earlierly which I have shown to all of you, this section our test geometry, this is this 100 millimeter and our 1500 as I build this geometry. The side wings, the left arm and the right arm are 100 mm. This ID, that is width is 6 mm, also the same here, downflow situation. So, the rectangle 2 is this. Now, I want to orient this rectangle in horizontal direction. So, I want a rotation here, I select clockwise 90-degree rotation and I want to position my this rectangle at 0 axis. I select and then select on click on build all objects and I click on zoom extents. This palette comprising of zoom extents, zoom box is used to zoom extents is used to view the whole geometry at a glance. Zoom box is used for specifically viewing our geometry, the particular section of our geometry. I want this section in above, that is at about 1500 mm. So, in rectangle 2 I choose my y coordinate as 1500 mm and select on build all objects and again click zoom extents to view the whole geometry at a glance. Now, I again click on right click on geometry and add my third rectangle. I give my input as 6, height as 100, 106 actually. Then my positioning as 1506. Rotation will be counterclockwise 90-degree and I select on build all objects. See, I click on zoom box here. We have finished building our geometry now. Now, one thing important to note is that we need to unite the geometries. Why union is important is that if we do not unite, the computation will stop at the very boundary of that individual domain, it will not progress. So, since we want to see how the simulation is going, how the flow pattern, which flow pattern will be occurring in this situation and through the entire geometry, we need to unite all these 3 rectangles here. I click on click in this geometry, again right click and we will find this Boolean and partition operations, click on union. Then after that we select all the 3 rectangles and click on build all objects. Now, our complete geometry has been unified. Now the second step is adding materials to our geometry. We click on, when we right click on this material part, there are 2 different options coming: add material, blank material, switch material link. These are basically documentation part. Blank material is used when we want to customize our material and add it into library. Add material uses the COMSOL multiphysics library and brings our material of interest. I click on this add material, a box appears here with add material and written on it. I type in here my first fluid, which is toluene, which is an organic fluid, organic liquid. Then I click on search. This process takes time, since COMSOL multiphysics environment uses 2 types of mechanisms to solve a particular problem. It goes for direct solution of a problem and it goes on iterative method of solving a particular problem. The advantage of direct method is that it is quick and it's accurate. It's build a set of matrices of our governing partial differential equations and tries to solve it in one go. It solves it in one go. There are 3 different direct solvers available in this COMSOL multiphysics. One is Pardiso, which stands for parallel direct solver, MUMPS for massively multifrontal parallel direct solver, then SPOOLS, sparse object oriented parallel direct matrix oriented solver. These 3 actually, the MUMPS, this solver can do cluster computing. You can divide it, divides its work into many nodes as the case may be, and searches for the solution. And in iterative solver we have GMRES, the best. GMRES stands for generalized minimal residual approach. So, in GMRES it is actually like the Gauss-Seidel iteration technique, which assumes a solution, then goes on iterating and stops until it meets the required convergence criteria. So, as we see there it has arrived. Now, click on toluene, then liquids, and I select, double click on, right click on this toluene and select add to selection. The toluene gets added. Now, our second material of interest, that is water. I type in water here and click on search and double click on water. Water has also added. Now, we want to specify which domain is containing which fluid. So, initially in this condition, our whole test geometry was filled with water, and from that left domain toluene was provided, the toluene inlet was provided, and the left domain was completely filled with toluene. As we have learned from our theoretical classes that the flow patterns gets affected depending on the initial wetting of the faces. So, we need to be very sure about the wetting properties and need to recheck them. So, then initialize these two domains with water, as was the experimental condition which was done, and this the left hand side domain with toluene. As I click on this particular domain, our in the checkbox the domain number gets added. This means that it has been selected. Now, we go on clicking the material properties, then choose to non solid, then again the same for the water portion, and click on material type non solid. Now, the material domain selection has been done. Now, we go to laminar two phase flow level set study, our study. Equation form, we choose study control, all the domains have been selected. These is basically a Navier-Stokes equation which it will be solving the continuity equation, and this is the level set equation which initializes the level set variable and solves for the interface and the whole computational domain. So, in this question I click on fluid properties. In fluid properties, the one thing very important to note is that for avoiding any kind of confusion, you should keep the material numbering and the fluid numbering the same, or else it will create a lot of problem. You might get confused. So, I click on this fluid 1 and check it as toluene material 1, and for the fluid 2 I select water. Then after that we need to enter here what is it will be my liquid interface. From experimental conditions I select here benzene, water, and other options are there. Library conditions I select user defined. Since measured by experimentally, our interfacial tension between toluene and water was 0.037. I type in here in this interfacial tension box 0.037 Newton per meter. Then after that I go on for selecting my the next part, very important part, is that to add inlet outlet interface to our geometry. So, when I right click on this laminar two phase flow, I get these options: inlet, outlet, initial values, gravity, etc. I click on inlet, what gets added. Since our geometry has having two inlets and one outlet, I need to select another inlet and an outlet. Then after that again I right click on this laminar two phase flow and add select the gravity, and then initial values too. What is initial values? That initially which fluid was present. Initially in these two domains, water was present. So, I select this fluid initially as domain as fluid 2, which is water. Then initial values 1, by default the other two values get overridden and one gets selected. Here it is already it's fluid 1. After that we need to specify our inlet, where the solver, multiphysics solver, will taking its inlet. I click on the zoom box and then I click on this inlet. Here the inlet demarcation gets selected in the check box. After that I need to specify my normal inflow velocity here. Here you can choose velocity field if you are having different spatial components in a velocity, or you can go for normal inflow velocity. I select here normal inflow velocity and type in as 0.07 meter per second. My inlet 1 will be completely consisting of the fluid 1, no fraction of fluid 2 will be present, I let it remain as 0, this volume fraction of fluid 2. In inlet 2, the inlet 2 will be completely comprising of fluid 2. So, I type in here 1, my normal inflow velocity 0.07 meter per second. I need to specify the domain, click on zoom box, again enlarge it and select this is my domain. Now, one thing important is to specify the interface, right click on that, the interface is already present here. Click on zoom box again and this to magnify this flow, and this is my interface here as was experimentally observed, initialized actually. Then after that initial interface has been selected, we have specified our initial values, inlet 2, inlet 1 has been specified. Now, we need to specify our outlet condition, the discharge will be at atmospheric pressure. Again click on zoom extends and go for enlarging my outlet, and I select this is my outlet. It automatically gets it gets added when I click on it. Then its pressure outlet, what is that is there are various options, velocity, pressure, laminar outflow. I select pressure outlet and I type in as 101,325 Pascal. During experimental condition no backflow was observed. So, I click in this check box that suppress backflow, and after that we need to add gravity effects to our system. Again zoom extends, select and then I can zoom box. Now, in these 3 domains my gravity force will be acting. So, I click on the 3 geometries and the 3 geometries get selected. This all the 3 geometries get selected. Now, this is the gravity vector, x axis is this one and y axis is the which is the 1500 length axis, that is this is y axis. So, in this axis my gravity is acting in this direction, going downwards, that is minus g hash constant, g is initially stored in the multiphysics environment as 9.81 meter per second square. So, then after that gravity effect has been added. Now, meshing part, as I explained earlier that this meshing selection of mesh size is very important to first go for a grid independence test, then after that mesh size we can be certain about our mesh size. There are 2 different options when I click on this is physics controlled mesh, user controlled mesh. User controlled mesh we give our mesh size here, in physics controlled mesh we utilize the multiphysics library for its different meshing criteria, and I select it as my meshing as finer. I click on build all. As we can see the meshing has been done, more dense mesh is present at the interface and less dense as the bulk. After the meshing gets completed, we directly go to our study part. As we have selected time dependent study, to specify time unit, when I click on this box there are different time units coming, nanosecond, microsecond, millisecond, minute, second. I select click on second as per the question. Then there is a range. It signifies that from what point, from which time we want to start our simulation and where to end with what time steps to. So, I give my solver that you start from 0 second, then go with 0.1 time stepping, calculate at 0.1, then 0.2, 0.3, then and like in this manner you end at 1 second. Results while solving, we click on plot. So, if you want to see the plot on how the volume fraction or the flow pattern is changing during the computation, we click on this check box here. Then after that we go for compute. In this situation actually there is a thing that it uses two, as I earlier said that it uses 2 different type of solver, that is direct and iterative method of solution. It is best to go for a for 3D or complicated geometry, it is best to go for an iterative method of solution rather than going for direct method solution, since for direct method solution your system might get hanged or it will slow down your system and it will not be so the progress will take some time and it requires a huge RAM for computing for going for direct solution. GMREs is the best iterative method for going for complicated geometries. So, as I have started the simulation, previously I have done some simulation, which I am going to present to all before all of you, the same in the same condition. This was my the simulation which I previously done with at the same conditions. With the known velocities, superficial velocities, we were not aware of the what flow pattern can prevail in this situation at atmospheric pressure discharge. And now we are seeing here that there is a slug flow. Slug flow is occurring. The red one is for toluene, the blue one is for water. So, this shows that, and it was also verified experimentally, and we saw that the slug flow was occurring in the real time experimentation. And in this way we can also extract the animation, and we can also extract the snapshots or the images of our slug at different time steps. These are the images of our slug at different time steps, that is 13.2, 13.3 seconds, how the slug is progressing with respect to time. So, in this way we saw, with given our input condition, we can extract or foresee our flow pattern, what flow pattern can occur in that particular set of conditions. Now, in our day-to-day requirement, we need to extract some graphs from our experimentation or some input which we provide. We need to extract some graphs, results such as pressure plot, velocity profile plot, and likewise. So, for this I am going to show all of you that how to extract a simple pressure plot across the length of the conduit. So, this is going actually progressing. Now, I click on results and data sets. For extracting any graph or graphical plot, first we will need to define our cut line. So, I click on data sets and select cut line 2D for its 2D geometry, and I specify 2 points, that is x I selected as 3 and y as 0, rather let it remain 0, and then after that 3, then this is 1506, and then click on plot. This is my cut line which is running through the entire geometry across the length of the conduit. I click on zoom extents, again click on zoom box. This cut line runs through the entire geometry, and I am going to specify the cut line for extracting results, and the plot will be it will take the values from this cut line. Now, again go for in the results section and I right click. There are different options: 3D plot group, 2D plot group, 1D plot group. I select 1D plot group for line graph here, and here is my selection 1D plot group. Again right click on this selection and go for a line graph. In this line graph, this is a line graph window. Now the solver is asking from where it should take the values. I give it as cut line 2D1 and then y axis data. In this icon, what data, what variable which we want to put in our y axis. I click on this icon and click on this laminar two phase flow node and select double click on pressure. I want to keep my pressure as y axis, and by default x axis is arc length, or which is the length of the conduit here. So, after this I click on this plot button. A plot has been generated here across the conduit, as we are seeing. This shows explains to you how we can extract a plot basically from our simulation. So, after this we need to extract some reports from our simulation. There is other reports which comes on multiphysics environment provide. We click on this reports option and then click on right click this report, that brief report, intermediate report, complete report, different options are there. Based on our requirement, we extract our report. One thing important is that it is showing that across the length of our conduit, that is this one, my conduit was initially this section, this 1500 mm section. Across this conduit, it is plotting the graph and showing how the pressure is changing with respect to the length. So, we see there is a linear evolution of pressure across the length of the conduit. So, in this manner we are going to simulate a 2D flow problem. So, we in this video we saw that how we can with given inlet velocities and outlet pressure discharge pressure we can simulate what flow pattern can be going or can be prevailing at those conditions, and to extract some simple graphs from our simulation. That is all. Hope that we will benefit, all of you will benefit from this video. Thank you.